Hello everyone, we the team Alibaba-Vision are going to give a brief introduction to our approach in this presentation. We are from Dhamma Academy of Alibaba. Alibaba Dhamma is devoted to the revolutionary in fields of economics, space technology, automatic control, computer design and manufacturing, etc. This is the outline of our presentation. In the following slides, I will describe the methods we used in FVC Track 1, including data analysis, data augmentation, training framework, post-processing, and finally I will show our visualized results. The train set of Track 1 consists of 19,138 images. We show the histogram of the pixel values in all provided masks. The x-axis indicates pixel value, and the y-axis indicates the number of pixels. For better visualization, we do not count the pixel value of 0 and 255. As shown in the figures, unlike other matting datasets, the distribution of FVC dataset follows an unusual pattern, may be caused by the annotating tools. We also analyzed the content of the training images, which included many hard cases, such as fluffy hair, motion blur, small floating windows, similar foreground and background, multi-person, passers-by. Our training data includes not only raw FVC data, but also the publicly available AZEG dataset, Adobe Matting dataset, and data which synthesized with complex background images. The advantage of introducing extra data is that it can increase the generalization of the model, while the disadvantage is that the annotating of extra data is inconsistent with the annotating of FVC data, so we will fine-tune the model on FVC data later. In order to enrich the diversity of data, we have adopted some data augmentation strategies, including general random cropping and flipping, color jitter, and varied blur strategies. We use these annotated data and a large number of background images to synthesize various training images. These background pictures are selected with salient objects but no people, such as bedroom photos with clothes or shoes, outdoor photos with cars. These data augmentation strategies improve the generalization and performance of our model. We adopt the simple but efficient UNet architecture to verify the effectiveness of different backbones, such as MobileNet v2, ResNest 50, and ResNest 101. And the results show that, among these backbones, ResNest 101 achieves the best performance. Therefore, we chose ResNest 101. In order to ensure a quick training and testing, we did not test other bigger backbones. We propose a strong high and low resolution representation pipeline for video conference matting, named HLF. In video conference, there are many complicated backgrounds with different scenes, illuminations and distractors. The similar appearance makes it difficult to recognize the foreground person and distinguish it from the background context. Motivated by some image matting methods such as SHM and GFM, we separately predict trimap and edge result. Specifically, we introduce an independent subnetwork to conduct a three-category classification: foreground, background and unsure area. Since the foreground person is always salient, we train it in a low-resolution setting and also apply a PSP module for global information extraction. The edge decoder is trained only for unsure area from trimap decoder. And in order to predict a detailed matting result, we fine-tune it in a high-resolution setting and dilation convolution is applied in the edge decoder. The final result is merged from the two predictions. Our training process includes 2 stages. Firstly, we pre-train the model on the training set with the MSE and edge loss, and then fine-tune the pre-trained model with the unary loss, OHEM and edge loss, and a pairwise loss. We compute the edge region by eroding and dilating the ground truth mask. OHEM only computes the gradient for the pixels whose L1 loss is more than 0.2 to handle the hard samples. We also add a pairwise loss to force the network to model the relationships of pixels in the local region. We verified the effectiveness of our loss functions on ResNest 50 and ResNest 101, and the results showed that they can significantly reduce MSE error. We adopt several post-processing approaches to further improve the matting results. We use flip predict and model ensemble to get stable prediction. In the following slides, I will explain 2 post-processing methods: remove outlier and interframe smoothing. We remove outliers in the predicted mask images via morphological operation. First, masks are binarized with a large threshold, which can remove false positive outliers with weak response. Then the binary mask is dilated with a large kernel in order to covert the matting area, such as hairs. Finally, the original mask is multiplied by the dilated mask to get the final result. As illustrated by this page, the slide pipe in background is predicted as foreground by mistake, which can be corrected by the morphological operation. We also use a smoothing trick to improve interframe consistency. The intersection over-union score is used to measure the movement between frames. If the person in current video does not move fast, we use the average mask of neighbor frames to replace current mask if current mask has jitter error. Finally, on the test dataset, a single ResNest 101 model reaches 0.00286, and then through the model ensemble, we reduces the MSE to 0.00197. The high-low resolution fusion further improves the result to 0.00186. The 2 figures at the bottom is a comparison of 2 methods. As you can see, the right picture has more sharp hair details. This is a demo of the final result. In the final leaderboards, we took first place according to MSE or grad. Here are our team members. That's all, thank you.